markets. It turns out there's another new ecosystem that's occurring in computation today, and it's called Docker. And Docker allows you to create what are essentially virtual containers. They are digital containers, and there's a whole series of different companies that have swirled kind of around there to enable this sort of Docker to manage these Docker containers. And what it's kind of like if you had your personal computer and we were to hit a button, suddenly if we were to make 100 copies of that or 1,000 copies of your personal computer up in the cloud, and with hitting another button we could make them all disappear or change them or whatever sort of transformations we wanted to make. That's what this allows. Well, it turns out that this is allowing a new form of automation as well. So you might know that back in 1908, when Henry Ford made the first Model T car, it actually wasn't built on an assembly line. It was actually built using the station build approach. And you can see the stations up there on the left. And in fact, when the first car rolled off the line, how much did it cost? $400,000 in today's dollars. It was not the car for the masses that he was hoping to build. But 5 years later, he rolled out this fixed chassis assembly line that we all kind of know about today. And it was about another decade. By the end of the decade, the price had gone from $400,000 to $3,000 in today's dollars for each car. That's how much that automation dropped, 130x improvement. This is had Ford's assembly line in 1913. 100 years later, this is the Tesla assembly line. And if you go and visit Tesla, as far as you can see, there's essentially no people. It's all robots. All the people are up behind glass offices programming the robots. And so this Docker infrastructure, this container infrastructure is kind of like if you were to go to an empty field and you were to suddenly hit a button and you build an entire automation factory from end to end. This is the Tesla Gigafactory. This will be the largest factory in the world when it's by square footage when it's complete. And then at the end of the day, you hit a button and the factory just disappears. That's what this Docker infrastructure allows you to essentially do in a virtual sense. And so for years, we used to talk about data liquidity, right? You flow data wherever data needs to go. And then we used to talk about elastic computing, where your computing just gets bigger when you need it. And then we used to talk about elastic storage, right? Where your storage just gets bigger when you need it. Well, we're kind of on the verge of a new type of liquidity. It's liquid compute, right? Where your computation flows wherever you need it. And today, these Docker containers will run on servers, they'll run on your PC, they'll run on your laptops. And how long before they begin running on your tablets, then your phones, then your watch, or even your light bulb, right? In your house will be running a Docker container. It'll be possibly crunching on someone's genome, in India, miles and miles away. So how do you build a global scale data strategy? How do you begin to kind of think about it? Well, my favorite advice is probably from Tim O'Reilly. He is the world's leading technology book publisher. And Tim says that the most successful companies he sees today are doing something he calls enriching their base layers. And the example he gives is of Google. He says, so you all remember when Google released Street View, where they filmed all the roads, and so now you can click the map and you can zoom in and look at it. Well, a lot of people, when they saw Google do that, they said, oh, this means Google's going to go into real estate advertising. So you're going to be able to look at people's houses, and there's going to be ads on the side and things like that. And the answer is, well, maybe. But recently, there was an engineer on the self-driving car team, and they were interviewing him. And they said, how is it that your self-driving cars are so successful? Right? You've driven, 1.5 million miles, and how is that possible? And he said something really interesting. He said, it's a lot easier to find a stop sign or to find a stoplight if you already know where to look. Essentially, they were using the Street View data that they already had to tell the car, there's a stop sign coming up, look in this area for it. There's a stoplight over here, start looking for it. And what this means is that this base layer that they built is now making other services better and more powerful. And Google has been almost a leader in this sort of base views, this enriching their base layers, right? What did they release? They released Gmail. Why did they release Gmail? So that they could get billions of email data that they could then build natural language processing tools on. And so they released, for example, Google Voice, right? Why? So that they could get all this voice data so they can enrich the base layers to build all these sort of natural language processing tools on top of that as well. And so the takeaway message is enrich your base layers inside your company. So then you might ask, well, how do we identify our base layers? Where do we even begin to look for them? And the answer, one answer, is capture your data exhaust. What is data exhaust? It's data that is just being generated from systems that are already out there. And one good example of this is, you think about the rise of this sort of wearables world, right? So we saw Fitbit and all these pedometers that you can wear and they track your steps, right? Except your steps are already tracked, right? With the phone in your pocket. It has a pedometer in it, it has a GPS chip in it, and so it can keep track of where you walk. It essentially has all the same data that's in your Fitbit, but you don't have to wear it. It's something you're already often carrying. And so in fact, a company created an app called Moves, which you may have heard of, which what does it do? Almost exactly what Fitbit does, but all you do is just download it, it's software, and it shows you how many steps and things that you took during the day. And then of course that company was acquired by Facebook, there are all sorts of companies that are now being created just based on data exhaust. Data that's just laying around. So you might wonder, well, how much data is out there, right? Forrester did a study, 63% of the data in our companies today is what they call dark data, unanalyzed. It's just sitting there. And this is something you have to make an explicit effort to go and inventory. No single person knows this. It's scattered information throughout, it's shattered across the organization. When we went to some hospitals, we found in one hospital no less than 300 different data islands that did not speak to each other. And so this is an opportunity of data that's just waiting out there. So you might remember that Amazon showed us sort of the value of the long tail, at least kind of brought to the forefront, where they had low volume products, but lots of them. And so because of the long tail, they were able to grow their company by about 30 or 40% on top of what they otherwise would target. Well, you can take this long-term, long-tail principle and apply it to the data science world as well. I'll give you an example. So you think about LinkedIn. What is LinkedIn from a data-centric point of view? Well, it's a social graph, right? It's a lot like Facebook. It shows who you're connected to, except for one problem. What happens when you try to connect to someone? What does LinkedIn tell you? They say, only invite people you know well. Well, what does that mean? It means that they are chopping off the long tail, right? If there's someone that you only saw once, or you met at a conference, or that just wants to connect for whatever reason, they're essentially cutting that out and just throwing that data out and not letting their social graph grow because they're trimming that. And so you might ask, well, how much is that long tail worth? Well, if you look at something like Facebook, it has 4 times as many users, and they were able to take that 4 times as many users and transform it into 14 times a larger market cap. And so it's for this reason, you probably saw when Microsoft bought LinkedIn recently, some believe that one of the reasons was because there was all this sort of data being left on the table. There was all this long tail value that was left. And this is the sort of value that's in our companies that we can find if we take this sort of inventory. So what's the principles here? Sunshine your dark data and capture your data exhaust, the data that you're just leaving behind. So Vinod Khosla, the co-founder of Sun, says that almost every company that he talks to has this summit that they're trying to get to. It's like summiting Everest, right? Their pinnacle, their goal. And he said, the key to summiting Everest is having a base camp strategy, right? Where you get to a particular base camp, that's where you build up your strength, that's where you build up your revenue or your resources that you need to make it to the next base camp. And many companies are missing this base camp strategy and these sort of fail-back plans to take a different path if a different path fails. When we were in when I was running the innovation lab, we used to draw these, what we call technology trees. If we could create this, then that would open up these possibilities. If we could create this, that would create these other possibilities. And so, so you might ask the question, well, how do you choose the summits that you're going to climb? And so this is Eric Horvitz. He's a senior distinguished researcher in Microsoft. He is the first physician that Microsoft ever hired. Bill Gates hired him over 20 years ago. And Eric says, you know, I showed up on Microsoft's campus the first day, and he thought, what have I done? Like, I'm a doctor, and all these people are computer scientists. What am I doing here? Like, how is this going to turn out? Well, it turns out, fast forward 20 years, every time you get a patent, you get one of these little stone cubes. Turns out Eric now has more patents than anyone inside Microsoft. In fact, if you go into his office, waist high and yay deep are all the stone cubes for all the patents that he has. And in fact, it's said that when they rebuilt Building 99, the research building, that they actually had to add additional struts underneath his office just to support the weight of all the stone from these patents. But if you ever talk to him, he is an incredibly brilliant guy where ideas are just coming off the top of his head, just like a fountain, constantly. And he says his favorite technique for deciding what direction to pursue is what he calls backcasting. He says a lot of people try to start from today and forecast the future. And he says, he says he doesn't do that. What he likes to do is forecast to what he calls the inevitable future. The inevitable futures that we all agree are going to happen. And then he says, then take steps one by one back to how did they get to that future? What was it before that? What was it before that? What was it before that? Until finally he sees a target map and he says, I think I can get to that spot. And then that's how he redirects and ends up tackling his particular projects to sort of create that future. The best example I can think of is, it's like Stephen Johnson's book, Where Good Ideas Come From. He says, we pursue the adjacent possibles. What are the adjacent possibles? And he says evolution is like an adjacent possible, right? It's like a giant mansion where there are doors, and evolution opens up one door, and then it opens up a couple more doors, and then you have to step from door to door. You can't teleport from one part of the mansion to the other. You go to the adjacent possibles, and of course there are all manner of companies today that are leveraging the new adjacent possibles. So, for example, Uber, right? What did Uber leverage? The rise of mobile, the rise in GPS, and the rise in app stores. And this allowed them to create entirely new services. So that raises the question, what are the new data science possibles, right? Because there's new ones happening every single day. And we talked a little bit about scaling data, and then we talked about scaling computation. But it turns out there's a whole new class of possibles out there. And what are they? It's in the area of machine intelligence. Machine intelligence as a service. And remember when we used to talk about products, software being released in beta, right? Look at this. These machine intelligence as a services are now being released in alpha, right? They're even earlier than what we did before. This is how fast this whole space is moving. There's all manner of companies that are now pursuing it. So for example, if you think about vision APIs, right? Vision APIs that your companies can use, what's out there? Well, here's just one example from just in the last year. This was a project. Remember when we used to say computers can't tell the difference between a dog and a cat? Yeah, look how far we've gone now. This is all the things that can be recognized from a single picture. There's green trees in the background. This is the leg of an elephant. There's rocks on the ground. This is a shadow on the ground. The elephant is standing. Here's another example from that same project. There's a man sitting at a table. There's a man wearing blue jeans. There's a woman wearing a black shirt. There's a white laptop on the table. All of this extractable. We've gone far beyond knowing what is a cat and what's a dog. Here's context search. The head of a giraffe, the leg of a zebra, a red and white sign, white tennis shoes, all can be searched into and extracted. It's also interesting to see when they make a mistake. So at the top, here's one I got right. A man in a black shirt is playing a guitar. That's correct. Or here's one at the bottom. A young boy is holding a baseball bat. Well, okay, not quite. It's a toothbrush, but it's a good start. Or a cat is sitting on a couch with a remote control. Okay, well, it's a ferret, but darn close, right? So that just gives you kind of a sense of how good these systems are becoming. Here's a project from MIT, Gaze Follow. We can now look at pictures and actually see where people are looking. And notice that this has implications for your cell phone because they can actually, within 2 centimeters, tell where your gaze is looking, which means you'll be able to control your phone with your eyes, just looking at it. This is what they're aiming to make possible. You may have heard of this company called Affectiva. This is it being used live, and you'll notice that every expression is being categorized in real time, and then they also try to assign the emotions to it. What does this mean? It means you put this into any application anywhere, and now the data exhaust you're getting just ambiently is the emotions of the person while they're using it, right? Imagine using your website and suddenly you see this is a frustration page, right? You just know that this is bad. Turns out the Google Vision API also allows you to look at images and pull out not only the things we mentioned before, but also adult or violent content, and also extract text as well. And this means, this is another company called Clara AI. Remember when we, like today on our phones, we categorize our photos by locations, maybe by people's faces. Look what we can categorize them for next. Next, emotions. They'll categorize photos by emotions and also ideas. So this means you could say something like, show me all the photos where I look like I'm humiliated. Delete those, please. Right? There's another form of data that's coming, and that's data from the sky, data from the cloud. And this is because from satellites, the number of pixels that we're getting is essentially increasing into the trillions of pixels. And this is opening up new areas of geoanalytics. What can they do? There's a whole new range of geoanalytics that are possible. I'll just give you a couple examples. There are over 1 million parking lots, 1.2 billion cars that have been tracked simply from space. We can look at parking lot occupation hour by hour, day by day. This company, Orbital Insights, also looks at world oil inventory. Right? It turns out that the roofs on the oil tanks are floating. And so what happens is that the lips of the tanks cause a shadow from the sun that can be picked up from space. So they essentially look at over 20,000 storage tanks in 800 areas worldwide, and they know what the world oil inventory is, even in countries that don't really want to tell us what their inventory is. We can tell. This is satellite images from space. You can see that Saudi Arabia has transformed their desert and added, they're taking water from underneath the desert and pumping it up to the surface. We can actually keep track of their crop yields and see these particular farms as they're creating them. And probably even more significant, we can do poverty mapping. We can actually not only look at agricultural productivity and car density, but building density and building height. It means that you can create a map in the developing world of essentially economic potential, where you might target the sort of next developing market. And there are all manner of Earth observation companies that are launching new satellites, and so we're just at the very beginning of this sort of exponential trend. So this is Forbes magazine, and these are a bunch of articles. And these articles have been written by someone by the name of Quill. So who is Quill? Quill is an artificial intelligence. It is basically a product of this company called Narrative Science. And so Quill writes financial articles that humans read. And Narrative Science says we're entering this new age, they call it natural language generation. And they say we're entering this new era of data storytelling, where the data gets converted into something that is human readable. So an example is, here's another company, AI Automated Insights. On the left, you can see the data, and on the right, you can see the website that's been generated from that data. Here's another company, Aria. They're doing the same thing, but with healthcare, right? They look at the data, they create reports for doctors, reports for nurses, and reports for that patients themselves can read. So some of you you're all aware of this sort of what's been called the rising 5 billion, right? The next 5 billion who are getting connected to the internet, and this opens up massive long tail opportunities for every company in this room, right? Well, then the question becomes, how do you scale your company to have interactions with these millions of new salespeople for your companies, right? There will be this super long tail, and you've got to communicate with them, and imagine your only communication to them may have to be through a cell phone. That may be the only way you can reach the seller of your product. How do you scale to manage a team that is that big and that diverse and that wide? Well, it turns out that we're entering kind of a new world where they call it the conversational economy. And you've seen just the beginnings of that with things like the Amazon Echo and Apple Siri, and you probably heard about Google Home recently announced. And now companies are releasing software development kits, SDKs, to allow you to write your own applications so that you can talk to these. But of course, this is in the developed world right now. But there are new APIs that are emerging that will allow you to target the developing world as well. For example, if you look at, I'll just talk about the Google Speech API. It has audio to text translation. It will translate into 80 different languages for you, and you can even take real-time streams and capture the data from that. Suddenly, if you get calls from people out in the field, suddenly this can be translated into text. And of course, they've also released something called Cloud Natural APIs, which also analyze the sentiment of the text. So is that a positive comment? Is that a negative comment? And also will break down the sentence. You may have seen this. This is Facebook Messenger. This is a new product they just released, and a new add-on to Facebook Messenger, a platform. It's in beta. They have over 900 million users. And notice that these are people texting, and they are interacting with a chatbot, right? With a company chatbot, and having entirely scripted sort of conversations with them. And if you think about it, this is the way you could reach all these people with feature phones across the developing world. This is the way that they'll interact with your sales team. This is the way how they'll order new products from you. And the infrastructure they're using at Facebook is this thing called WIT AI, where if you notice, you type a sentence, and it automatically recognizes what times are so that you can extract that data, and then you can write programming code against it. So now the question becomes, how does your company keep up, right? There's products that we're talking about that are released every single month, every single week. Some of these things are still in alpha and beta. How do you possibly keep up and build stuff here? And I think one of the best examples I've seen, or my favorite example, is from Pinterest. So Pinterest realized that of these 50 billion pins, when people pin things, they often aren't really interested in the entire picture, right? They're interested in something in the picture. They're interested in those shoes, they're interested in that purse, they're interested in that lamp. There's something in that picture. And so, and the problem is that if you try to search for this lamp, let's say, and I'd say wiry, polygonal, black metal lamp, well, it doesn't work very well to try to find, things like that if you wanted to ever buy it. So they wanted to be able to allow you to just drag across the picture and search for something that looked like that. And the way that they were going to do this is through a deep learning approach. And as you may recall, or know, that with deep learning at the lowest layers, first you essentially learn the curves and the lines. Then in the middle layers, let's say you're training on faces, the middle layers, you actually learn the eyes and the nose, the features. And then the top layers, those are assembled to create a face. Well, what do they want to do? They wanted to throw out everything on the bottom, throw out everything on the top, and keep the middle layer as descriptors. Because they were convinced that these descriptors include things like wiry, lacy, the colors, these are adjectives. And so that was their approach. The problem is, they had no deep learning people in their company. So what did they do? They took 3 people from the development team, and then they joined with 2 students and a professor at Berkeley, and created a team of 6 people. And then they built this search engine using these deep learning techniques. Well, how well did it work? Well, here's me dragging the picture to search on it, and these are the results on the right side. Way better than the text results. And so you might ask, how long did this project take this team? 6 months, from beginning to end. And so what's remarkable about that is that now 40% of the searches on Pinterest are from this tool that was built by just 3 people inside their company. This is the sort of value that can be created by these sort of exponentially rising technologies. And so this is why this concept of ivory towers, where people disappear for 4 years, into college and then they come out afterwards, is now being replaced with ivory bridges. Every successful company is going to have these ivory bridges where they will have partnerships and they'll be working with the students as they learn the technologies as they go through. So the takeaway here is build those ivory bridges. And in fact, even in our in our media lab, our innovation lab in healthcare, we had 12 slots for 3-month rotations with PhDs to just pull them in and build projects like these. So one thing that happens in projects is that our project knowledge grows as time goes on. And you've probably been on one of these projects. Where do we make our decisions about the project? Right at the beginning, right? We try to make all the decisions we can right at the beginning. And of course, it's when our knowledge is at the very, very lowest. And of course, there becomes a time, way back here towards the end, where someone has another idea and people say, why did you have that idea 6 months ago? It's too late. We can't go back. And so what we want to do is actually have our decision curve match our knowledge curve, where you delay every decision you can as long as you possibly can so that you have the most amount of knowledge when you finally make it. This, essentially what they aim to do is to create what is the cost of change. You want to make the design to allow zero cost of change. Because then if someone has an idea towards the end, it's like, fine, okay, we change directions. This is an explicit design decision that you have to make before your data science project begins, that we are going to aim for zero cost of change design. I'll just give you an example. So you've probably seen on college campuses or other places where they spend months and months and months planning out where the sidewalks go, right? Then they put the sidewalks out, and then what happens? People walk everywhere else but on the sidewalks. So what do? They take an approach called late binding, where instead they just lay down all the sod, then they let people walk wherever they want, and then they go in afterwards and put the sidewalks where the people walked. And then of course what do you end up with? Pristine lawns as a result. So this late binding approach can be applied particularly in data science projects. And I'll give you an example. This happens often where people ask, what standard are we going to use? Right? What standard are we going to exchange data through? And the thing about standards is they say the great thing about standards is that there's so many to choose from, right? And so the answer is no, we're not going to choose a standard. The answer is if you can store numbers, if you can store text, if you can store binary streams, you can store everything. And later, you can go in and extract the meaning that you need from it. It's a lot like we build skyscrapers today, right? We let people move into different floors, even while other floors are still being built. You can build the same sort of data scaffolding infrastructure for your own data science projects. So one question people often ask is, do we need big data or small data to solve our analytic challenges? Perhaps the best example of a big data win was this Google Translate contest, where they just destroyed the competition, right? They came out of the blue, they won 35 out of 36 different categories for a translator that translated into Chinese and Arabic and back. No one on the team spoke either one of the languages that won. And in fact, the algorithm that Google built was the simplest. What did it do? It relied on big data. It relied on billions of web pages that were out there that were in 2 different languages, and it looked for the phrases that closely matched, and then that's what it showed as the result. So this has often been shown as a big data success. And there's been some studies that have looked at how much data you need and how much your accuracy improves. And as you get more data, accuracy improves, except for one problem. All of these graphs were for natural language processing tasks. For human language, where you have to understand the breadth of human language. If you look at other data science projects like this one, remember when Netflix was trying to predict, they released that data set, they wanted to predict what movies you would watch and like? What happened is they added more data. They got more accurate, more accurate, more accurate, and then it went flat. And even when they added more and more data, their accuracy went down in their models. And they have some of the best data modeling scientists in the world. And so it turns out that if you go to Kaggle.com, where these are contests, data science contests that your companies can run. You can sponsor these contests and tens of thousands of people will compete in them. Every single winner of all the hundreds of competitions they've had has won using small data. They haven't required big data. And so the answer is you can generally win with small data. There is one exception, and that is deep learning. Deep learning often requires lots of data. Not always, but in many cases, it's a very hungry algorithm. For example, the Facebook's deep face recognizer trained on 4 million faces. Its first round. It's now been trained on over 1 billion. So years ago, we were trying to capture 3D data on people's bodies, and we were looking at this system called IntelliFit, and it cost tens of thousands of dollars, and it was very interesting to us, except look at where we've gone today. Autodesk has released a free app where all you do is take a picture of an object in a bunch of different angles, and what it will do is automatically stitch those pictures together and automatically create a 3D representation of that. This is the state of the technology. And so where will all the cameras be to capture this sort of stuff? Well, maybe you saw the University of Stuttgart just 3D printed a microscopic 3D camera. It's 0.12 millimeters in size. The optical cable is the thickness of 2 human hairs. Basically, it costs pennies to build. What does this mean? It means that these type of cameras could be absolutely ubiquitous everywhere, and we could be capturing this sort of camera image data. I had a professor in undergrad who was an expert in bats. And one day he came back to the lodge, and a fan was spinning, and he saw a bat flying between the blades of the fan. Despite our slow mammalian brains, that just shows how accurate and how fast and how simple echolocation must be. And we have this question today, right? How will drones be able to navigate the night skies and not get caught in wires and not get caught in bushes? The answer is something like echolocation. And it turns out that our cell phones today, using the microphones and speakers, can actually do echolocation. This is a project called Finger.io, and here he's tracing a shape, and it appears right on the phone. Here's another one where he's tracing it on his arm. The smartwatch is doing echolocation. And so, of course, what does this mean? It means it won't be too long before every single robot in our home, every single device, will be able to be pinging out and getting 3D data. This will be data exhaust available to every single one of your companies. And in fact, we're moving to where the room itself is the sensor. You may have heard that every time your heart beats and you breathe, it bends Wi-Fi signals. This is a group picking up a baby's heart rate and breathing from the crib around her simply because it's bending Wi-Fi signals. That means the rooms itself will be streaming this data and it will be available to us. And so companies like, for example, Emberlight, which is a plug-in above the bulb, means everywhere you see a bulb, you could plug in another device that suddenly is capturing data. So the last thing I'll mention is some Christmases ago, I decided to pursue this project. And the idea was to take and create digital DNA and use that to create neural networks. And I remember having this sort of Frankenstein moment where I looked at my screen and all these little creatures were moved around by their own brains, where they were suddenly alive. This is not the project, but this is similar. And it was this kind of sense of the power of evolutionary computation. And that stuck with me until years later, we were inside our innovation lab, in one of our innovation labs, and we decided to try to do predictions. So these are volumes of customers, and you could never predict what the volumes are going to be using something like Excel, right? But now you can see as the system evolves, it fits the curve tighter and tighter. You can see its predictions in yellow and how good it does. These are creatures that are just evolving. And we discovered it's very good for simple, for when you just want a single button to predict something when things are very, very complex. And we've evolved. There was a project some years ago where they tried to evolve structure as well as function. And so, for example, they evolved creatures that could swim. And notice they look a lot like things we may have seen swimming before in the water. And then some things look even more like things we've seen in the water. Then they evolved things to walk. And of course, the results of these looked like children's toys that people were never quite imaginative enough to create, and yet they're able to move around, and yet this is how creative evolution was. And what's remarkable is when you watch them, it looks like they're struggling. It just, whatever they can do to reach the goal, in this case they have to reach the red dot, as if they're not going to live if they don't. And of course it's evolution. They won't live if they don't. And so here's another example of a creature that evolved a propeller. right? A structure we don't even typically see in nature. It was able to evolve this. And it turns out that you can use these to simulate all manner of different phenomena wherever you have a fitness function. And so you can evolve them to walk upstairs or climb trees or navigate different disasters, essentially, situations where you wouldn't ordinarily see this sort of behavior. And what's remarkable is these things scale. They scale to your computation. If you only have a couple of Docker containers, let's say, then you simulate just a few organisms. But then, as you get more computing power, you simulate more. But of course, as Moore's law clicks around, then suddenly you can simulate on a global scale. And as Moore's law keeps going, suddenly you can simulate on a galactic scale. And you might wonder, well, what could we really evolve? And the answer is, well, pretty much everything that we see in nature today could potentially be evolved. It's why you may have seen Elon Musk say, odds are we're probably living in a simulation. Is because of this sort of possibility. And so what is the next form of machine intelligence? To me, it is this evolutionary computation, which is unlocked through high fidelity simulation. The moment that we can begin to simulate the things going on in our organizations in high fidelity, that's when we can unlock the power of these sort of systems. So the bottom line and the takeaway is that there are more adjacent possibles now than ever before in human history. And this, of course, means great opportunities for the things that you're building today and the impact that you're going to have tomorrow. So thanks so much for your time.